Hi everyone! In this video, we'll talk about strategies for integrating mixtures of sine and cosine. Here's a typical example of what I mean by that. When a power of sine is multiplied by a power of cosine, there's a reliable strategy that we can follow for finding an antiderivative. The first thing you should do is identify the odd power if there is one. If sine x has an odd power, then we let u equal cos x. And if cos x has an odd power, then we let u equal sine x. If neither of them have an odd power, then we need a different strategy, which we'll talk about later. In this case, we can see that the power of cosine is an odd number, which suggests that we should let u equal sine x. So let's go ahead and try this, and we'll see why the strategy I proposed works out well. So start by calculating du, which would be cos x dx. And because of that, it would be desirable if we had cos x dx appearing in our integral. If we did, then that entire section could just be called du. And we can make that happen just by splitting up our cosines. Originally we had cos cubed, but if we split off one copy and reserve it as du, then what remains would be cos squared. And we haven't done anything yet with the sine squared. So what you see here is the same integral we were given, but I've just written it in a way that makes our substitution a little more convenient. Now if we carry out the substitution, sine squared can become u squared, and cos x dx can become du. The only problem now is that we have these cosines left over, which need to be expressed in terms of u. But u is sine x, not cosine x. Thankfully though, we can use a familiar trig identity to express cos squared as 1 minus sine squared. And that would just be the same thing then as 1 minus u squared, so this actually gets the job done pretty nicely. All that remains now is to expand everything out and antidifferentiate. So I'll leave it to you to pause and check these remaining details as necessary. We can see that the strategy I proposed worked, but I'd like to take a moment to talk about why. The key to solving this problem was to apply this trig identity so that everything could be expressed in terms of u. But to use this identity, we needed to have a cos squared, or more generally, an even power of cosine was necessary. And we did have an even power of cosine, but only after we formed du. We actually started with an odd power, but making this substitution left us with an even power, and that's ultimately what made it possible for us to apply an identity and solve the problem. So hopefully that gives you an idea of why the strategy I proposed is what it is. Let's try the same ideas in another example. You can see here that we have an odd power of sine, so according to our strategy, we should respond by letting u equal cosine. That probably seems like a weird substitution, since the function given to us doesn't even appear to have any cosines, but this actually does work, and to see why, let's work through the details. To start with, calculate du by taking this derivative. Now, since du takes the form of sine x dx, I'd like to make sine x dx appear in my integral to make for a nice substitution. And we can do that by splitting off one copy of sine x, as you see here. With that, sine x dx can really be called negative du, according to the substitution that we made. So after pulling that negative out in front, we're left with this integral. At this stage, we still need to do something about the copies of sine x that are still left over, but unfortunately, u is cosine x. So this is where we hope an identity can be applied, just like the previous example. And that's going to be possible here, but only because the remaining power is even. Notice that's a direct consequence of the fact that we started with an odd power, hence the importance of looking for an odd power to solve these types of integrals. Let's write down the identity that we want to apply. It's important to notice that this is specifically an identity for sine squared, but what we actually have here is sine to the 4. So before we can apply our identity, we need to express sine to the 4 as sine squared squared, as you see here. After that, we could replace sine squared by 1 minus cos squared. And since cos squared is the same thing as u squared, we end up with this reasonably nice result. Before we get our antiderivative, we need to expand this out into the form of a polynomial, and that requires FOIL. So pause and check that you get these results after expanding, and after that, the rest is just a straightforward antiderivative. So you can check these remaining details as necessary. You might wonder what we should do if both sine and cosine have an odd power. But in that case, there are really two possible options. On one hand, we could let u equal sine x due to the odd power of cosine. And on the other hand, we could let u equal cos x due to the odd power of sine. Either of these will get the job done just fine. But it turns out one of these is a bit easier than the other, so let's just try it both ways to see which of these is the better option. First, we'll try u equals sine x so that du is cos x dx. To make cos x dx appear in our integral, we'll split off one copy of cosine so that this cos x dx we see now can now be called du. With that, we can say sine cubed is the same thing as u cubed, and we've got our du, but we still have this leftover cos to the 8 to deal with. We really wish these were sines rather than cosines, so for that reason we're going to apply an identity. Before we can do that though, we need to express cos to the 8 as cos squared to the 4. After that, we know cos squared is the same thing as 1 minus sine squared, and 1 minus sine squared is the same thing as 1 minus u squared. So this was a successful substitution, and all that remains now is to expand everything out and antidifferentiate. That part is not very enlightening, and it's honestly a little tedious to expand out that power of 4, so I'm going to skip the details here. Now let's see how this would have went if we instead let u equal cos x. In that case, du is negative sine x dx, so for that reason, we should split off a copy of sine x so that we can use it to form negative du as you see here. After doing that, we could pull out the negative and express cos to the 9 as u to the 9, but we still have this sine squared left over, which is really already set up to be expressed as 1 minus cos squared. And that is just another name for 1 minus u squared. So after that, all that's left is to expand everything out and take your antiderivative, which is really the easy part. When you compare these two methods, I hope you can see that our second attempt is the better method here. That's because our first attempt would have required us to expand out this power of 4, which isn't exactly hard, but it is annoying. So here's a tip that we just learned from doing this. If you're in a situation where both the powers are odd, it's easiest if we let u be whichever one has the higher power. In this case, cos x had the higher power, so letting u equal cos x led us to the easier solution, although both of them were possible technically. After doing all these examples, we know what to do when we see an odd power, but what do we do if there are only even powers? We're going to talk about that in the next video, so look forward to it, and I'll see you next time.